Okay. Yeah, so for a review, what we should do is we solve this type of equations by comparing the index when they have the same base. So our goal is to make them the same. I mean the base are the same. To make them the same, we need to apply the exponent rules. So we have like, if we multiply two exponents, we have the addition of the, I mean, we multiply two numbers, we have the same base, then it is the same as adding their exponents. While in this case, see, so we are at page 7. Yeah, so for this one, our goal is to make the base the same. Sorry. Yeah. Yes, yes. Yeah, we take the power, the exponent, to negative. Mm, uh, if we take the power negative one, we need let's say we need to flip it. So we have this say 7/6 is equal to the reciprocal, and we take the power negative one. Yeah, but and from here we also need to be careful about the big bracket. So this one we need to multiply the whole. Yeah, so means that over here we need to uh, multiply the whole bracket, but not just the first x. Okay, because if we multiply, we'll skip one of the seven. There is, it will affect the answer. Okay, so yes, the answer is correct. Wrong, and for what you made, for the mistake you made at the first part. So we need to replace this 7/6 to this 6/7, and we take another power negative one. So from the first line, we replace this 7/6 to this 6/7. I mean 17/6 to this 6/17, and we have another negative one. So we have another negative one here. But uh, we also need to consider the x minus 7. So we have another bracket to the power x minus 7. Okay, yeah, yeah, it's the same. Yeah, it's also okay. So these two are the same actually. Just by the what by a rule we know that if we have a to the power b to the power c, we can write it as a to the power bc. So yeah, but if we have two brackets, is maybe not in the syllabus, I guess. Yeah, so actually you need to remember to multiply the two exponents. Okay, and then next we have two same base, so we can now compare the index. Okay, so we have 2x equals to this, and we will get x equals to 3 over 7. Okay, wow, for one this one we need to determine whether the statements are truth, whether they are always truth, or sometimes, or it will never be truth. So this one we actually need to so what says find the actually this one we will need to draw the graph. mm, so yours is, so actually what you need is you need to say that this statement, okay, uh, so this statement, is it always truth, or sometimes, or never truth? Okay, mm, yeah. So in this case, the r can be any number you can set it. So if only if it is only has no solution for any r, then means that it is, I mean, so so let me explain again. So this one is if it is if the statement is true for any p, q, and r, then it is always. But if there does not exist any PQR, so that this statement is truth, then it is never truth. So so in this case, I can explain the first one first. So let's say we draw the graph of this p to the power x. So is this one. So so because p is larger than 0, we know that this curve is in this form, where it passes through this, the y-intercept is 1. Well, we also know the equation qx plus r is a line, right? So we can write the so we can draw this line because q is less than 0. We know that the line is some sort like this form. So it is like what's it? It is from is in this direction instead of this green color direction. So this green color direction is when the q is larger than 0. While this one is when q is less than 0, we have this type of line. Okay, so this is so we will discuss the solution by this graph. Actually, it's quite it's simpler if we use this graph instead of like do some calculation. So we have qx plus r, where the pqr is real numbers. So if for every pqr that has no solution, means it is always truth. But we know that for some, like for this case, the p, for any p, okay, and then for q, c q, okay, so q is less than 0. So if we choose this q to be uh so any q, let's say 1, and then for r, if we choose the r to be equals to 1, so it when r is equal to 1, so we know that this line will pass through this point, right? This y-intercept. I mean, this line has y-intercept 1. So means that this line qx plus r, uh, this line qx plus r is equal to px, p to the power x. If we choose this situation, uh, so means that the equation has solution, because the intersection of these two graphs will mean that we have a solution for this equation. So actually, the equation is has no solution. It is never truth, because if we have one line in this form, okay, so for every p, right, the curve is always in this type of form. But if q is less than 0, this line will always be pointing towards the left side. While for any r we choose, even though if r moves down to like this part, it will intersect the exponent graph at some point. So means that it is never truth. Okay, so for the next one, maybe you can try to like follow me like the to use this graph to determine whether it is always or sometimes. So let me see, is there any other equation? Solution is equal to 0. Okay, uh so I will open the next page. So we have p larger than 0, q larger than 0. The equation has more than one solution. So let me write. Okay, so px qx plus r. So p larger than 0, q larger than 0. So we have more than one solution. I mean, if then you have more than one. So from in this case, what we need is we need to draw the graph. So the same thing, p to the power x is this type of graph, while the qx plus r is also a straight line. Well, note that q is larger than 0, so this line is like pointing to the right side. So it's something like this one. But now we see that for some r, this line is below the exponent graph, then we have no solution. Because we will not have any intersection of these two functions. But if we choose the r to be somewhere over here, then we can get an intersection of these two graphs. So this indicates that we have more than one solution. So means that the answer would be sometime. Yeah. Yes. Yes. So yes. Yes. If they are equal, then we have only one solution. If it is less, then we have no solution. So it is not always truth or never truth. So it is sometimes truth for this statement. Okay, well, for the third one, let's see. So for the third one, so maybe you can try to like draw the graph for the third one. Okay, on page 10 for the x is 0.4. Yes. Okay, and then for question 10, it is we have a number 1 on the right hand side, which means that the index should be 0, and we can solve that x is equal to 2. Okay, so page 13. Okay, so same, we should make them the base the same, and then we can compare the index. Okay, so 9 to the 1.5 power. If you can deal with the decimal points, you can change it to fraction. And for the 9, right, it can be written as 3 to the power 2. So we have 3 to the power 2 to the power 1.5. Okay, uh, so 2 can multiply by 1.5. Okay, okay. So next page. So we need to solve this one. So next one is we have two if we have a to the power b times a to the power c, we can simply find it by adding the index. Okay, if you forgot, I can explain why we need this one. Is, let's say we have uh, a times a times a, we have b times, so we have b times of a, and then we multiply a times a times a. While here we have c times, so we can simplify it as a to a times a times a, where we have b plus c times of the multiplication. So that's why we have the power to the a to the b plus c. So actually, this power rule is, I mean, this addition means that we can uh, add the index because we have b times, we have a number of multiply of b times and another and c times. So the total multiplication that we need is b plus c. So we can write it as a to the power b plus c. So from here we know that 2 to the power 3 times 2 to the power 5 over 3. So we can write this one as 2 to the power, so we add this one 3 plus 5 over 3 equals to 4 equals to 2 to the power 4y. So now we can write 4y is equal to this 3 to the 1 3. So it's 9 plus 4 is 9 plus 5 is 15. 14. So here we can find that y is 7 over 6. Okay, so this one actually is the same solving way, the same way we deal with the previous question, but we need to be careful for the about the multiplication and the square root, and we need to compare the index only when we have two terms, each one on one side. Because if we compare it when we have three terms, we cannot cross out the terms and if we have three terms. Uh, and this one, right, is from here to here, this number becomes this number is also because it's also very weird because the cubic root is for the whole 2 to the power 5, while it's not affecting the 5. Yeah, so this is what we need to be caution about. And now we'll have the next. So not sure, have the school discussed the geometric sequence? Okay, so I will like give an intro. Okay, so a geometric sequence is let's see. So a geometric sequence is some sort, like we have a number. Let's say we have a number a. Okay, a. Oh, okay. So and then for the next wait, so I need to explain what is a sequence first. So a sequence is a, a set. I mean, we have a sequence is like we have some numbers that they are in some sort of a sequence. So they are in like A1, A2, A3, A4, where the n term we call it the AN. Okay, so a geometric sequence is when we have the an term to be the a0 term, or we say a1 times r to the power n minus 1. Okay, so means that from the second term, the relation of the second term and the first term is we multiply by a number, or we say that a ratio r. So each term we multiply by r, and we multiply by r. Okay, so this multiplication by r, so we can have a general form of each sequence, I mean each term. So we have this a to the power n. I mean an, the n term would be the first term multiplied by r to the n minus 1. So if you see when n equals to 2, right, we multiply r one time. Okay, one time. So if we have n equals to 3, we actually multiply the first term by 2 times. While if n is equal to 4, we multiply by 3 times. So we see that if we have 4, we actually only multiply 3 times. So if for the n term, we actually multiply by n minus 1 times. So that's why we have this an is equal to a1 times r to the n minus 1. So actually, a geometric sequence is just each term we have a ratio. So the ratio means that the previous term and the next term we have a ratio between them. Okay, so for example, we have 1, 2, 4, and 8, and so on. This one is the geometric sequence. It's a geometric sequence. Geometric is geometry. I mean geometric. Yeah, geometric sequence. With the first term a1 equals to 1 and the r is equal to 2. Yeah. Yes. So it's actually So it's actually exponential because, but we only consider the integer value. Wait, let's see. Yeah, we only consider the exponential. Yeah, it's an exponential, but we only consider the index to be an integer because you can see that uh, the index only differs each other by 1. So, but actually it is a part of the exponential exponent graph. I mean the exponential function. So so that's why they include this geometric sequence inside the exponent function part, because uh because it is actually part of this section. So from here, maybe you can try some of the questions. So to find the ratio, we can take the second term to divide by the first term, so we can find the ratio between each term. What? No, we are on slide 1. Oh, so your answer is times r equals to 4. Oh, sorry, I did not see that. Yeah. Yes, yes. So the so actually to answer this question, you need to write the next three terms, right? Yeah. So next three terms and graph the sequence. Mm, yeah. So to write the next three terms, we take the 192, so 768, and then 323072 and 12288. Yeah. While for the graph, right, actually you can just do a sketch. So for this graph, we actually only need to plot. Okay. Graph the sequence. So actually, if we wants us to graph the sequence, we cannot draw the whole function, because to graph the sequence, actually we will need to plot only for the integers. So when so actually only need to plot this 3 and then 12. Graph the sequence. So from here, when x equals to 1, 2, 3, so we only need to plot these points 1, 2, and I mean 3, 12, and 48. So yeah, because it means that we need to graph the sequence, so only the points that are the member of the sequence need to be plotted. Yeah, but if you uh but they are actually on the line. Yeah, they are actually on this blue line, where the blue line is something like 3 times 4 to the power x. Okay, so we can find that actually this blue function is 3 to the power, I mean 4 to the power x times 3. Okay, so next slide. So actually the same question that we need to determine whether it is arithmetic, geometric, or so. In this one, actually we can see that the ratio can be negative. For actually, I think there's something on the first slide. Actually, is r equals to 4. So because this is not the xr, this is multiply. So I use the x to represent multiplication. Okay, so this times. Okay, so it's not XR, but we only denote R as the also this X I also need to take away. Yeah, so it's actually dot R. I mean, so it's A times R, but not the X thing, where the R is the common ratio. So in this one, I see that your answer is R equals to 4, but it is not correct because uh, remember that we need to determine the ratio by only two consecutive terms. So we cannot skip like from the first term to the third term. Okay, so this is an geometric sequence. Okay, uh and then the next three terms would be negative. So we have negative 8. So we have positive 16, negative 32, and positive 64. While actually to graph this one, maybe is something like this. So we have 1, and then negative 2, 4, and then negative 8. But we cannot graph it out. I mean, we cannot write out the function, but we know that it's something like, yeah. Yeah, but actually uh there is some discontinuity on the point where we have the x to be like 1/2. So because when x is equal to 1/2, we have the numbers negative square root 2. But actually we know that the square root can only have positive numbers inside. Because like we have, when we multiply two numbers, either it is positive, we can get a positive number. If two numbers they are negative and we multiply it, they will result in a positive number. So for a square root of a negative number, we cannot obtain a real outcome. Okay, so that is something like uh maybe you learn later. Yeah, so we cannot graph this negative base function. Yeah, so because the negative function, it will have some discontinuity, uh, and is uh, always jumping up and down is not not easy to graph actually. While for the next one on slide number 3, so to find the ratio, what we will do is to take the second term and divide it by the first term. Yes. So the ratio. Oh, so yeah. So it is not a geometric sequence. Okay. So since negative 18 divided by 9 is negative 2, but this 27 divided by negative 18 is uh, 2, 3, 3 over 2, negative 3 over 2. So it is not a geometric sequence. Okay, so the other parts is left as an exercise, and we will discuss them next class. Well, so for the recordings, right, you can watch the replay of the video